What's up, guys? It's me, Sir Ernest, and today we will discuss a sample problem related to Hamiltonian dynamics. The problem reads: use the Hamiltonian method to find the equations of motion for a spherical pendulum of mass m and length p. Okay, so this is our figure. So previously, we've discussed plane pendulum, wherein our pendulum is only constrained or is constrained to move along one plane. In this case, we have a spherical pendulum, so we have a secondary degree of freedom, and that is our phi direction. So in spherical coordinates, theta and phi are your two of the three coordinates. So we know that for spherical coordinates, the coordinates would be r, theta, and phi. Okay? So, in this case, our r would be this direction, and this is a constant. So, r would be b, and that is a constant. So, please take note of this. Okay? So, in this figure, we already said that this is our reference point. So, this will be our origin. Okay? This is theta, and this is b. This is your mass m. Okay? So, in spherical coordinates, the velocity is already given by r dot r hat. We have already discussed this before. So, that's r dot r hat plus r theta dot theta hat plus r sine theta theta dot phi dot phi hat. So we already know that b is equal to r, or r is equal to b, and that's a constant. So therefore, the time derivative of r will be equal to 0. So we cancel this. Okay? So that means the velocity is now simplified to b theta dot theta hat plus b sine theta phi dot phi hat. So therefore, the speed, or the square of the speed, will just be the sum of the squares of the components of your velocity. And those components are b theta dot for the theta direction, and b sine theta phi dot for the phi direction. Okay, so the square of the velocity will now be equal to b squared theta dot squared plus b squared sine squared theta phi dot squared. So therefore, this gives us the kinetic energy as 1/2 m times this one. So this is b squared theta dot squared plus b squared sine squared theta phi dot squared. Okay? Now, so you will notice here, let's go back to our problem. Okay? The height of the particle m, or particle with mass m, will be h. So that means, okay, so if this is your kinetic energy, the potential energy will now be written as U equals mgh, and this is equal to mg times negative, because the direction is downward. This is where your potential energy is 0, so that means this is y, or is equal to 0, or h is equal to 0 here. Okay, so this is negative h, negative b cosine theta. So this is negative mg b cosine theta. And here we take note that u at height 0 is equal to 0. So therefore, the Lagrangian becomes L is equal to kinetic energy. So here, let's distribute 1/2 m, or m over 2. So this is 1/2 m b squared theta dot squared plus 1/2 m b squared sine squared theta phi dot squared plus mgb cosine theta. So this is minus, L is t minus u, so this is plus. So as you will notice that L is only a function of what? It's only a function of theta, theta dot, and phi dot. And these are all functions of time. So therefore, from the Lagrangian, we can now get the generalized momenta. So it's momenta because we now have two generalized two coordinates, or 2 degrees of freedom. So this will give us p theta, and this will give us p phi phi. Okay, so remember that when we calculated the generalized momenta for a plane pendulum, we ended up with getting the angular momentum, your usual angular momentum. So let's see how this system is different from that. Okay, so let's start with p theta. So p theta will be the partial derivative of the Lagrangian with respect to theta dot. So this is equal to, so theta dot, so this is the only term for the Lagrangian that has theta dot. So the answer is m b squared theta dot squared, which is what we got when we dealt with our plane pendulum. Okay, so this is your usual angular momentum. Now, what happens if we calculated the generalized momentum in the phi coordinate? So this is now equal to partial derivative with respect to phi dot, and this is equal to, this is phi dot, so this is equal to m b squared sine squared theta. Okay, so phi dot. Okay, so this is not your straightforward angular momentum, but because this is also an angular direction, or angular component, so you will see here that we can rewrite this as m b sine theta squared phi dot. And what is this b sine theta? B sine theta would be this direction. So this is b sine theta. Okay, so essentially p phi is the angular momentum along this direction. Okay, so it's consistent to our previous result. Now, p theta will give us theta dot, which is equal to p theta over mb squared, whereas p theta will give us theta dot equals p phi, phi dot equals p phi divided by mv squared sine squared theta. Okay, and we're going to use that to calculate our Hamiltonian. Now, let's compute for the Hamiltonian of the system. Okay, let me fix that first. Okay, so Hamiltonian. Again, Hamiltonian of the system would be H equals sum of Pi Qi dot minus L for all I. So because we have two coordinates, so we have P theta dot plus P phi dot okay minus our Lagrangian. Okay, so you will notice that if we're going to substitute this and this to our Lagrangian, okay, we will end up with minus okay, let's write this first. Okay, so this is minus 1/2 mb squared theta dot squared plus 1/2 mb squared sine squared theta phi dot squared plus mgb cosine theta. Okay, so substituting our phi dot and theta dot in this equation, we now have okay, so you can do the algebra later. So we now have P phi squared over 2 mb squared plus P phi squared over 2 mb squared sine squared theta minus mgb cosine theta. Okay, so if we're going to compare this, okay, to our total energy, we can actually compute the total energy, and this is actually equal to T plus U. Okay, so here we see that the Hamiltonian is a function of theta, P phi, and phi, P theta and P phi. Okay. Okay, let's go back here. So if we're going to compute for the kinetic energy of the system, here, substituting this phi dot and theta dot in terms of the generalized momentum, will end up with this. Okay, and of course the potential energy would be minus mgb cosine theta, and this one. So this is actually U, and this is T. That's why it's called T, and that's why we concluded that the Hamiltonian is equal to the total energy. Okay, so now going back to our Hamiltonian. So our Hamiltonian, okay, is now given by this equation. Okay, so now the equations of motion. Okay, we now have, okay, first we have now a Okay, again, so let's rewrite first the general equation. So we have q I dot is equal to partial derivative of h with respect to p I, and then negative p I dot is equal to the partial derivative of h with respect to q I. Okay, so let's apply this. Okay, as you will notice that we have 2 degrees of freedom, and for each degree of freedom we have 2 equations of motion, 2 equations to describe the equation of motion. So let's start with theta. Now theta, from here we now have theta dot, and this is equal to partial derivative of h with respect to p theta. So from here, so p theta, this one, and the rest is not dependent on p theta. So it's now equal to p theta over mb squared, which is what we got earlier. Okay, and then the next would be negative so let's okay, let's do the phi dot. Phi dot would be derivative of h with respect to phi. So phi dot is equal to derivative of h with respect to p phi. So this is p phi. So the result is p phi divided by 2 m. That should be m only. Sorry about that. So this is m b squared sine squared theta. So which also is consistent to our computations earlier, which is your angular momentum along the phi direction. Okay, so let's try this one. Okay, so let's start with theta. Okay, so negative p theta dot would be equal to partial derivative of h with respect to theta. Okay, so this is now equal to, okay, so where is theta here? So theta here and theta here. Okay, so let's differentiate this first. So here, so that's theta means, so that's sine to the negative 2 theta, then bring down negative 2, so this is negative sine, so negative p squared over 2mb squared times sine, so that's sine negative 2 minus 1, so that's sine to the negative 3 theta, then differentiate sine theta with respect to theta, so this is cosine theta. Okay, and then theta here, so this is negative, so that's plus mgb sine theta. Okay, so let's simplify this, and this is equal to okay, so let's start with this. That is positive, so that's mgb sine theta minus cosine theta over, sorry, no more 2 here because we already brought down the negative 2 here, so it will cancel with the 2 here. So there should not be any 2 in the denominator. Okay, so that's cosine theta over m b squared sine cube theta times p phi squared. And what's p phi squared? So that's mb squared sine squared theta phi dot then squared. So this is mb squared sine squared theta phi dot squared then squared. Okay, so this term is actually this term, and this term is actually this term. Now on the left hand side, you now have, this is negative time derivative of p theta, which is m b squared theta dot. Okay. Okay, so let's simplify this. We now have negative mb squared theta double dot. So remember, m and b are constants. And this is equal to mgb sine theta minus, so m squared will cancel with m, so m will be retained here, and so is b squared. This is sine squared squared, so sine to the 4th theta divided by sine cube theta, that's sine theta. And then we have cosine theta here, and then phi dot squared. So therefore, the equation of motion becomes theta dot equals negative g over b sine theta plus sine theta cosine theta phi dot squared. So this is our equation of motion in the theta component. So how does it happen? So again, remember, we could see here that m will be cancelled, and then one of the b's is also cancelled. Okay, now let me write it here. For theta, so this is negative for phi component, so that's negative phi dot equals derivative of h with respect to phi dot. It should be phi. Okay, so as you notice here, that the Hamiltonian is not a function, or is not an explicit function of phi, so therefore this is 0. Okay, so what does it mean? It means that phi is a constant, and this is equal to mb squared sine squared theta phi dot, and this is a constant. So here, the momentum along the phi direction is a constant. Okay, whereas phi here along the theta is not constant, because this is not equal to 0. Okay, so these are the equation of motion of your simple spherical pendulum. Now, let's look at the results here. So you will notice here that, okay, let's go back to our problem here. So you will notice here that if, for example, the pendulum is not revolving about the vertical axis, so that means phi dot is 0. So when phi dot is 0, okay, so this is 0, this is 0. So p phi, or the Reynolds momentum along phi, will be equal to 0 naturally, and this case, this will now be reduced to theta double dot equals negative g over b sine theta, which is our equation of motion for a simple pendulum. And that is precisely what happens here, because when phi dot is equal to 0, so that means it doesn't, this particle does not revolve around this axis. So that means this particle will just swinging in one plane. Whatever plane that is doesn't matter. The point here is that if this particle is not revolving like this, so that means this spherical pendulum will now be reduced to a simple planar pendulum, and the equation of motion will be like that. Okay, so that's it. So thank you for watching. I hope you learned something today, and I hope to see you again in the next video. Bye bye.